Now, anything you do you need to measure, that is a very important, and there must be some way of quantifying things, and we are going to address in this module Ecg, Eeg, Emg, Edg. These are basic ways of measuring certain parameters of the health conditions of human beings, and that is what we are going to look at it. So, it will basically be oriented towards applying some electrical and electronic principles and designing these sensing instruments and devices. That will be the thing I think I will.
Yeah, the first 1 hour we will talk theory, next 1 hour we will do the designing of the Ecg amplifiers. Basically everybody remembers op-amps, that is what it is, op-amps, okay, differential op-amp, instrumentation op-amp, and then one high pass filter, one low pass filter, okay. So, to know why we want to use that, we will see. Basically biopotential is, as the name, you know, in electrical engineering, mostly in engineering, the names are self explanatory, right. Biopotential is the potential of biological systems such as cells, tissues, organs between any 2 points, okay. And if you wonder where does this potential come from, okay, we know no every cell has, okay, it needs for its survival calcium, potassium, sodium, chloride and various other molecules, okay. Typically inside the cell we will have more potassium and then less sodium outside, okay. And whenever the gates open, okay, the sodium and the potassium transaction will happen. When that happens, you know, no, the charge, you know, no, in the body the conduction is ionic conduction, okay. So, it is all ions. So, the charging will be different. So, inside if you measure the potential with respect to, okay, outside, the inside potential will be more negative, okay. That is why we get our resting potential, action potential, everything negative, okay. Negative 70 to 100 millivolts is the normal thing. And then of course any impulse happens, okay, something suddenly like cardiac impulse, brain impulse happens, the potential will increase, okay. That is whenever there is a impulse occurs. Biopotential, I will show you. I am going to repeat this many times, just I give. Normally I use a board, I explain here, I do not, that board I need a good writer, that is not good. Huh? So, biopotential is the potential between any 2 points in our body. It can be a cell, it can be a tissue, it can be an organ. Okay. We are interested to measure that potential. For example, we want to measure the potential of cardiac, the heart, because that gives you the heart electrical variations, which tells whether the heart is working properly, okay, whether the, you know, it is beating above the 60 or below the 60. So, they basically give a very precious or very valuable data, okay. The electrical activity of various organs is the biopotentials. The electrical activity of heart is called as ECG, electrocardiogram, okay. The electrical potential of brain is called EEG, electroencephalogram. The electric potential of muscles called electromyogram. The electric potential of eye, electrooculogram, like that, okay. Say they give, and then we will see what are their magnitude, how to measure it, okay.
These potentials are different?
Slightly different, yes, yes. Because remember the brain function is different, the brain cells are different. So, the amount of calcium, potassium, sodium, chlorine will be different, okay. So,
ocular is it?
Electroocular is for eye. So, yes, they are different, they better be different, otherwise if you measure, how do you know whether you are measuring heart or brain or eye or muscle, okay. So, for biopotential, potential of biological systems, you know, why there is a potential, because the concentration of various ions are different, okay. So, and then why we are interested in this, they will tell us, for example, if you have a what do you call epilepsy, you know, the then that will be studied using our brain EEG. Okay. Similarly, by having EMG we can put electrodes and then applying pulses we can enhance, we can regenerate the activity of our body. So, there are many applications of that. Okay. So, we want to see what are their magnitude, what are their frequency, and then how to build them. So, today we will do the designing and tomorrow afternoon we will build them. Is this clear? Okay. So, we will see that. Okay. So, what are biopotential? It is the electric potential that is measured between points in living cells. Okay. Remember, everything we talk is living. If you are dead, we can use it for some purposes, but not for most of the purposes. Okay. Dead is also important. Okay. Living cells, tissues and organisms, okay, and it accompanies all biochemical processes. Okay. Again, this potential depends upon the electrochemical concentration. Okay. We will see more in the next 2 slides. And this describes also the transfer of information between and within cells, okay, between cells, within cells, this is a measure of it. And then measurement of potential indicate valuable clinical data, okay, that is the main thing. Okay. Here is the neuron. Okay. Neuron will be, if you see, neuron is not just a small cell, it will have a nucleus and then it will have axons and many other things. Okay. And then this is a muscle impulse, here is the nerve impulse. Okay. So, typically you will be in the negative 70 millivolts. When there is an action happens, it is called depolarization, increase. Okay. For example, heart will pump, correct, it has to contract, okay, pump it and then it will come, that is, okay. So, all that is called depolarization. Then comes the repolarization, coming to the normal state. Okay. So, depolarization means increase in voltage, you can know that much, and in the case of heart it is caused by the contraction. I think all of you know how heart works, correct? It will collect the blood, okay, the right side will collect the blood and then contract, send it from atrium to ventricle, which contracts, send it to the body, and then the other side will collect lung, okay, it will send. So, pure blood will be sent to the other parts of the body and then the bad blood will be sent to the heart. Okay. So, we will have 2 chambers, atrium and ventricle, and each one will have 2 of them, left ventricle, right ventricle, left atrium, right atrium and all those things. Okay. I would not go into details because in 1 week it is not possible to learn them thoroughly, but you can just hear it. Okay. And then how do this potential arise? Remember we were talking that you have the cell, inside the cell, outside the cell, cell membrane is the protection. Okay. Mother nature made it, cell membrane will have lot of proteins, receptors, everything. Okay. In this case we do not have to worry about it, all we have to know is inside. See, you see there will be lot of potassium inside, lot of sodium outside. Okay. The sodium is not good for health, all that. Okay. So, we want potassium especially for instant energy. Okay. So, concentration of potassium ions is 30 to 50 times inside, okay, whereas the sodium ion is 10 times outside. Okay. And then whenever there is an impulse occurs, there will be transfer of or transmission of these 2 ions. Okay. So, in the resting state the member is permeable only for potassium ions, okay, they only can go and come normally, okay, at resting stage. Then potassium flows outwards, okay, leaving an equal number of negative ions inside, correct. Potassium is positively charged, potassium is positive, sodium is positive, calcium is 2 plus positive, chlorine is negative. Okay. So, this will give rise to the various potentials. Then electrostatic attraction pulls the potassium and chloride ions close to the membrane. Okay. So, when you measure the field across it, you will see, okay, it is with respect to outside it is negative, with respect to inside it is positive, it is how you call. We are interested in the magnitude, we do not worry about the polarity. Okay. So, electric field is directed inward, okay, and then the electrostatic force versus the diffusional force. So, if there is a chamber, okay, there is a membrane, okay, inside and outside, the electrochemical gradient will cause the ions to move. When the chemical gradient reaches the equilibrium, they stay at that state. At that state, what will happen? The outside potential will be different from the inside. That is how we get that equilibrium potential. This was invented by Mr. Nernst. He is a Nobel laureate. He came up with the equation to calculate that equilibrium potential, okay, using this equation for only one ion. Okay. Then came Mr. Goldman, Hodgkin and Katz. Again these two got Nobel Prize, he got Nobel Prize for this, these two got Nobel Prize for this. They come, remember the cell does not have just only one component, it has many components. So, they will using this one, this is the permeability coefficient, it is the concentration, I for inside concentration, O for outside concentration.
A means what can be, what it can be?
A is it's a different kind of ion, we are not interested in it.
Chlorine.
No, they are, it is, if you see there is somewhere it's there, I cannot offhand, I do not know. It is a protein, it is a protein with a negative charge. We do not.
A actually could be coming from an amine, okay.
Amino acid.
Yeah, it could be amine, that is how it is coming. It may be what is the protein? Protein is also a amine.
No, amino acids are proteins, correct. Yeah, but our concentration here is potassium and sodium. Okay, those two only major components, who they are the major players. It is like Dhoni and Gole, everyone else is supporting.
In equilibrium, outside charge and inside charge will be equal.
Equilibrium is electrochemical equilibrium. Okay, so the concentration of the ion, the components will be the same, but not the potential. Okay, the number of ions inside and outside will be the same, like calcium, but not the potential, because when the concentration is same, the potential will be different. Okay, that is what. Okay, so Nernst equation, and actually this is called GHK equation. If you have your smartphone or laptop, if you put GHK calculator, it has an app. Okay, so you put the numbers, it will give the output very nicely. We will play with all that after the break. Okay. So, do you understand biopotential is the potential between any 2 points in our body, living cell, living tissue, living this one, and then this is made. Okay, this potential is made because of the ionic difference. Okay, the ionic charge difference, the valence. Okay, they call valence also. Okay, that is because the inside of the cell, outside of the cell. Okay. So, basically if you see this equation, R is what? R is the gas constant, E is the temperature in Kelvin, Z is the valence, F is the Faraday's constant, logarithm of CIK. Okay. In this case potassium. Okay. C concentration inside, concentration outside. Here permeability, remember the how much potassium can pass through, how much sodium can pass through, they vary. Okay. So, this is pK, permeability of potassium inside, and then permeability of sodium inside, and then permeability of chlorine, okay, and then comes pK, E out. Okay. So, we have to know each one of them, they are typical numbers available. So, knowing all this we can calculate. Okay, here we know the solution. When you do the calculation, what should be your V, Vm or Vk, whichever the equilibrium potential, what is the value you should expect when you do this kind of calculation, especially GHK equation? What should be your output voltage? What is the magnitude? What is the range? Can you get negative 200 something? What is the resting potential value? Negative 70 to 100 millivolt. Okay. So, if you get too low, you know something is wrong, because they cannot be too low, they cannot be too high. Okay. So, I will tell in my class students, if it is there you can put a 0 and give me the paper, I do not have to grade like that, okay, because many times that is the kind of knowledge I want you, okay. When you see something you should know, yes it is correct, no it is not, okay. The number punching anyone can do, okay, the getting that knowledge, okay. So, you know that membrane potential should be between negative 70 to 100 millivolts normally. That is when I said when it is cancer it will become minus 15 to 30 millivolts, okay. So, that is the range. Then from minus 70 it will reach negative 55 and then it will reach positive 20, that is the depolarization, okay. The sodium potassium channels will open and then they will come back, okay. That is your heartbeat, we will see that, okay. So, so far everybody is thorough, biopotential, value of biopotential.
You can put a diagram there and markers are there.
No, these diagrams will be much better. I will come.
What is F in equation?
Yeah, Faraday's constant. I will give you all those numbers. Okay, Faraday's constant, gas constant, temperature. Okay, so it will vary with respect to temperature, correct? Yeah, yeah. We will do some examples. Did we go through this one?
The Nernst equation, does it describe the potential?
It gives the equilibrium potential for a given ionic concentration, for only one. That is when you know GHK they came, because how can you just do only one ion? Your body has many. That is how they both got. Cass didn't. These two got he got Nobel Prize because that was the original invention, and they got because they modified it. Yeah, all this one is you know even Ecg, William Beethoven, he also got Nobel Prize because these are all you know breaking inventions, you know. Okay, so when membrane stimulation exceeds a threshold level of 20 millivolt, from negative 50 to 20 millivolts, the so called action potential. When it is here, it is in resting. When there is any stimulation, any impulse occurs, something happens, and then your body will act, react. Mostly it will react. So, from negative 70 it will reach a negative 55 and then it will go to plus 20. At that time sodium potassium ionic permeabilities of the membrane changes. Sodium ion permeability increases very rapidly at first, allowing sodium ions to flow from outside to inside. Remember, inside is potassium, outside is sodium. Now because of this action they will go rush into the inside, making the inside more positive, before it was negative. Then the more slowly increasing potassium ion permeability allows potassium ions to flow from inside to outside, because you are getting more sodium, you have more charge, you have to compensate it. So, slowly potassium ions will come outside. So, thus returning the membrane potential to its resting value. They will get if there is any impulse, they will react, then come back to original position. So, this is what here it is. Negative 70 or 100 to 55, and then they will rise to plus 20 and then slowly come to original value, and then if there is any other impulse they will move. Make sense?
First impulse is of nanosecond, like
Impulse, anything whatever the brain feels, senses. Nanosecond does not come here.
no first impulse in the
First impulse?
There are two impulses.
Yeah, first it will go from minus 100 to negative 55 and then it will go, and
He
then
is trying to ask you what is the duration for that. Is there in a
duration it varies, we will see that. Yeah.
Like two impulses here. What is the significance?
Normally you do not get two impulse, in this case they showed. Typically you will have from negative 100 to, you will have small like this. Remember, the impulse will not be exactly the same all the time. So, they will vary. So, for example, take your cardiac thing, you will have that P wave and then PQRS complex, then T wave, and then U. This is U, this is T, this is P, sorry, this is P, Q or S complex. Okay. So, typically what will happen, you will be in here minus 70 to 100, okay. Then you will reach minus 55, this is 0, then you will reach and then you will come down. So, in between something can happen, okay. This and all it is not easily explainable, at least not I am. So, if you want we can, you know, in one course that professor, anything you ask question, that will be a good homework problem, okay. So, maybe I will follow his style. I will try to find out, you also find out, because you don't know the body won't react every time the same, okay. The number of ions flowing through an open channel is more than 10 power 6, okay, 1 million per second. Body is a inhomogeneous volume conductor, and these ion fluxes create the measurable potentials on body surface. Oh, sorry. Okay, here ECG, okay. First we will see ECG, electrocardiogram. Also if you see other slides I will have EKG. The Germans invented initially, the theory, the history comes later, okay. They called electrocardio, they use K. You know, no, US, Americans, they want to change that. So, they use EC, cardiac, okay, CA. So, you will see both because some doctors still call EKG, some doctors, most of them call ECG, some people call EKG. Okay. It measures the electric activity of the heart, okay, well known and traditional. It is first measured by August Wöhler, okay, in 1887. But it was made more fully in 1895, okay, William Bothevin, and he only got the Nobel Prize, he did not get it. Okay. It is very widely used in clinical environment to diagnose your heart condition. Okay. So, the number of heartbeat, the height of P curve, the area of the what is that P QRS T complex, okay, QRS complex, and the distance between, okay, PT interval, PR interval, everything will give you about your heart condition. Okay. So, when we do measure this in the lab, normally you do not get perfect wave. So, everybody will tell you are going to die because your heart is not good. So, you will see that tomorrow like that. Okay. So, here is your Ecg waveform, okay, P, it is the contraction of the atrium, and then QRS complex is the contraction of the ventricle pumping the blood into the body, okay, and then they come down to the original shape T, okay. You will see all these in the next slides, and then U. Normally you do not use U much, I do not think anyone uses U, it is still there. Okay. So, this PR interval, okay, where it ends, where it starts, this PR interval, and then the ST segment. You see the name P curve, QRS complex, then PR interval or PR segment, ST segment, okay, QRS interval like that, okay, then QT interval, ST interval, okay. All this gives you volumes of stories. Okay.
This is to the atrium, not the, you said this QRS is for the ventricle,
Yeah.
and P is for the atrium, is it?
Yes.
Do we not associate anything with the auricle? Because the heart, if you see, there are basically 3 chambers, 2 auricles and 1 ventricle which is called as septum.
Basically 2 chambers, one is left ventricle, right ventricle, left atrium, right atrium, 4. It comes. Yeah, I am giving which are all I feel is important, everything is there are 70 slides. Okay. Anyway, whatever I can cover up to 4 o'clock, then we will do the design because we will not have time. Okay. So, this is for your reading pleasure tonight. So, ECG amplitude 1 to 5 millivolts, And if you want to measure this, and you want to display it, obviously you cannot measure 5 millivolts in digital, okay. If you remember olden days they used that paper chart, we are not talking there. So, how much is the minimum value you need for the computer to give the output? What is the minimum the computer needs to show an output? What is the minimum? You are all electronics, correct? What is the minimum you need?
Processor.
Huh?
Processor you are asking.
No, for display. What is the input to any digital system? What is the minimum value? You need at least 2 volts.
minus 32, 7.
That is higher, 2 volts. You need minimum 2,
Over the range.
0 to 5, correct? So, you need at least 2 volts for it to display anything, okay. Then plus minus 15, the tunnel is there. So, we have to convert everything to at least 2 volts, 1.5 volts, okay. That is where your amplifier comes into picture. Do you understand? Because our heart, how much? It's a pump, but it's not the pump which can pump the water from there, in the tongue, but it pumps the whole body. It seems the circulation, the blood circulation is like twice the, what is the circumference of earth? 25,000 miles. Our blood travels 60,000 miles, more than twice the surrounding of the earth. So, imagine that, okay. And then the bandwidth, the frequency is 0.05 to 100 hertz, okay. So, you can see that it varies so much. So, if you have to build a band pass filter, because you have to filter any frequency below 0.05 down, okay, you have to cancel it, and then any frequency above 100 you have to leave it, okay. So, we will have one low pass filter which will allow only below 100, we will have one high pass filter which will allow above 0.05, okay. But remember this 0.05, it can be 0.048 and all, because remember our R and capacitor and the resistor values decide finally, okay. And then what could be the error? Remember we are going to do it in your lab, there will be your 50, 60 hertz, your lights, your wires, so they will cause interference, and also motion artifacts, okay. If you are moving anything, that will cause artifacts, okay. And then typical applications, diagnosis of ischemia, means the irregularity of the heartbeat, okay. Then arrhythmia, again this is whether it beats high or low, okay. What is the normal heartbeat? 72 to 90, what is the unit? Per minute. So, what is the frequency? 1.2 hertz, okay. So, that is the typical, okay. So, here we are wearing, very good. These are all your quiz, okay. What are all numbers I give more significance, you can remember, okay. So, yeah, we know these are all the details, we have to skip now, when time permits we will come back. And we are going to use only 3 lead. We will put 2 in the chest, 1 in the ground, and that will be connected, okay. The 2 goes to your op-amp, okay. It's the 2 will go to, we will use a differential or instrumentation op-amp. So, you will have 2 inputs, it comes from here, and then the ground, okay. So, we are going to use that one only, because this is old, and here you can see why is it obsolete, okay. So, 90% of the horse electric activity can be explained with a diphode source model, we can just measure it anywhere. By the way, I met one professor in IIT Madras, he was working, remember if you are a burn victim, okay, there is a fire accident, you are all burned everywhere, how are you going to measure ECG for you? So, he was measuring, putting on the seat, in the chair, he was putting electrodes everywhere, and just that fellow will there and measure that one. So I did not see the result, but he was talking about it, a master's student project like that. So, we can measure the biopotential, especially ECG, in many ways. Next is the electroencephalogram or encephalography. Encephalogram is the output, the graphy is the technique, okay. It measures brain's electrical activity from the scalp, we cannot go inside. Actually, that is what some people do, for especially you want to control epilepsy, they drill and put an implant, a small pulse generator, which will be preventive. Okay? It will sense, remember before you get a epilepsy seizure, you will get some, which one? Yeah. In Seattle, one person, he was, it seems per day he will get 30 or so seizures. Using this he only gets 2 or 3, so he is working for Microsoft because he can go travel and come. Before that he cannot leave the home. Okay? So they implant it. We do not do that, we will just put it as much as possible. There are many students there with a bald head, so they will get nicely, others here to wipe, and I will tell them just shave little bit and put like that. Okay. And then this signal results from the activities of billions of neurons. Okay. And then see the magnitude 1 microvolt to 10 microvolt. So again we have to convert it to at least 0.5 2 volts. So you can see the imagine the amplification we need. And again here the frequency is 0.5 to 40 hertz. Okay. So here also you will have 50-60 hertz power line interference, thermal RF noise interference, and then blink. If you blink also it will blink. So when you make all this tomorrow, you have to be very careful. Stand still. Okay. So we will have 2 people grow batch, so that one person is the measurement, other person does the measurement. Okay. And then typical application sleep studies, know this snoring, and some people will not have it. And many times you remember, did you know the accidents happen because people fall on the wheel? Okay, in US 13,000 people die each year, I do not know here, maybe more. Okay. So people are working on how to sense, using EEG, your sleeping pattern, and then when it comes.
You are talking about the people falling asleep while driving or something?
Correct. Yeah. Because these drivers I read to bring that jasmine flower from Madurai to Chennai, because they pick in the evening, fresh it has to be. Okay. So they leave around 7, 8, they have to be here by 1 o'clock. So they drive like something, it seems. They get per trip 600 rupees, that is a lot of money per night. Okay. Because the flower has to be nice and blooming and smelling, otherwise no one will touch it. Okay. So like that. So if you do 2, 3 because you want more money, you ride many times, that is it. Okay. So sleep studies, seizure detection, and cortex. The cortex is a very important part of the brain. So how it varies. Did you know, this, like I read this few years ago, this all Google and other big boys, they implant, okay, sensors in your brain, and then you go to Walmart shop. When you see something, you like it, the light bulb will be on, then that sensor. So they want to see which customer likes which one, and then follow them and do that. So these were all there. For money people do anything, but we will do all this to make people's life better. Okay. You can use the sword to kill someone, to cut the fruit. Okay. You know what we want to do. So again they use 10 to 20 leads. We won't use this much, but if you want you can use as many leads you want. We did it with 2-3 leads, it worked. Okay. We don't.
What is the optimum number of leads?
There is nothing. It says 10 to 20. Depends upon whether you are in a GH or in a private hospital. There is nothing. Remember, none of this. There is no standard, no optimization, no nothing. People like you and I will study all this. The doctors, the more they put, the more time they can charge more. Who cares about optimization? Electromyography, okay, for regeneration we can study the electromyogram, okay, because by giving stimulation pulses, okay, we can get that our invertebra to do some work. This fellow, he was like below hip, he cannot do anything. They pulsed him like how many pulses, maybe more than 10 pulses. That fellow could stand for a few seconds. Okay, so they are still working on it. This is again in Louisville. That is the paper in IEEE, we will get that paper. Okay. So in this case 1 to 10 millivolt, okay, and bandwidth is 20 to 2000 hertz. So this is my favorite because it is easy to remember. So one of the question will be compare and contrast the amplitude and frequency of Ecg, Eeg, Efg. Okay. So, Ecg, you know what is the magnitude? 1 to 4 millivolt, frequency is 0.05 to 100, Eeg 1 to 10 microvolt, okay, and then 0.5 to 40 hertz. This is easy. 20 to 2000 hertz, 1 to 10 millivolts. Okay. Again, pardon?
Audio range.
Oh yeah, correct. So you can see that, you know, there can be lot of 20K, but still it is audio range. Yeah. So you can have more errors. That is why I told you, my students put everywhere and they have a lot of fun time. Each one will go put everywhere, and one fellow want to put here and here and here, and oh God, they enjoy this kind of labs. Okay. Muscle function, neuromuscular disease, prosthesis. Okay. This is for to build, when you put the prosthesis to move your feet and all, they will, how do you know whether the muscles is moving? So you have to measure electromyogram. Okay. So they put the electrodes. So we normally put one here, and then we measure it, but you can measure anywhere. Okay. So basically you need to know what is the amplitude, what is the frequency, what is the application, what is the error. So that when you measure, you try to avoid that kind of error. Make sense? Questions? Everybody is thorough? Very good. I will see it after some time. Okay. Electrochemical, if you see, it is very difficult. I do not take chances, who will come to measure the electrical activities of eyes. Okay. So we do not do it, but if for the completion of learning, okay, the amplitude is 0.01 to 0.1 millivolt, bandwidth is DC to 10 hertz, okay, very small bandwidth. It is because of the movement of the eyeballs. Okay. The potential varies in proportion to the amplitude of the movement. Okay. In many ways a challenging measurement with the little clinical value, because we cannot measure it accurately. For on the contrary, ECG, EMG, EEG will be very commonly used in clinical diagnosis, whereas this is not that much. Okay. This is useful to find eye position, sleep state, vestibulo-ocular reflex, okay, all those things. Primary sources of error include skin potential and motion. Okay. So remember, we are going to put it on some part of the muscle, so it will have that. Okay. So you need to distinguish between whether it is a myogram or EOG. Okay. So anyway, I never measured this, I did not take chances. Okay. This is from Dr. Mandel. Okay. So I thought I will talk about it. He gives a nice history. 1842, Italian scientist Carlo.
Where is Dr. Mandel?
I do not know, MD, DM, DC.
No, that is okay. Where?
No, I go to the web, no, as a professor you are allowed to use this for educational purposes, only you cannot make money out of it. So I get the free ride. Okay. 1842, Italian scientist Carlo, how do you pronounce? Whatever, Carlo M realizes that electricity is associated with the heartbeat. What about, when did we first find the frog has the beat, and then we found the galvanic potential? Do you know what is the period we did that initially? Was it before that or after that? And then in 1876, Irish scientist Murray analyzes the electric pattern of frog's heart. Okay. Actually we started with the frog's leg, right, that is, it twitched. That is how they found. Okay. Then comes 1895, William Einthoven, okay, created for the invention of the EKG. He is from Germany, they use EKG. Okay. 1906, using the strong electrometer EKG, William Einthoven diagnoses some heart problems. String electrometer. Okay. 1924, Nobel Prize for Physiology and Medicine. Okay. 1938, AHA, American Heart Association and Cardiac Society of Great Britain, defined the position of the chest leads. Okay. But no one follows the 12 lead anymore. 1942, Goldberger increased the Wilson's unipolar lead voltage by 50% and made augmented leads. Again we do not use this, at least not in this course. 2005, successful reduction in time of onset of chest pain and PTCA by wireless transmission of ECG on his PDA. So, this is how big initially it was. Okay. They started and we follow that. So, tomorrow you will see how small, okay, and how cheap it is. Just how many? 4 op amps, 11 transistors, sorry 11 resistors, 2 capacitors. Your ECG is there, and you know GE builds this, they charge $10,000, okay, because they put bells and whistles, the computer, they put it on a cart, okay, so they charge like nearly $10,000. Then they realized they can reduce it, okay, remove all those hi-fi things. So now they are selling for $3,000 of course, okay, with the computer and the cart and the thing. And tomorrow you bill and see how much cost it happens, okay, and then how we can make it cheap and better, okay. Anyway, thanks to that $3,000, which is like 1 lakh, you know, 1 lakh, 1.5 lakhs. Remember it was made few years ago, at that time it was only $40 I think, now only $66. So many, okay, village clinics could buy this, so that they do not have to go to city, okay. So many people die because they could not find out anything. So this saved, you know, the $3,000 saved it. Yes, that is so we can make it even $1,000, it is worth it, because the computer will cost some money, right, even $2,000 still it is cheaper. Okay, so that is what my goal is, okay. I will tell everyone whoever builds and makes money, be my guest, okay. So here is your, again you see, no, there are a lot of activities, I do not know whether we want to go through it, okay. So you know the PQRST of the ECG, and here is, you see, you put 2 of these and then you put a ground, this goes to ground, these 2 goes to the amplifier, 2 leads, and then you do the amplification and filtering, comes out your ECG, okay. This is what we will do tomorrow. And okay, now it will, all your questions will be answered, okay. And ECG or EKG is a device which graphically, okay, records the electrical activity of the muscles of the heart, okay. It is used to identify the normal and abnormal heartbeats, first invented in the 1930s, we know all that, okay. Okay. The heart is composed of 4 chambers which make up 2 pumps. The right pump receives the blood returning from the body and pumps into the lungs. The left pump gets blood from the lungs and pumps out to the rest of the body, okay. This is the contraction and everything. So each pump is made up of 2 chambers, atrium and ventricle, okay. So left ventricle, right ventricle, left atrium, right atrium. The atrium collects the incoming blood, and when it contracts, okay, that is the depolarization. Contracts means the voltage will remember it is pushing it, voltage will increase, okay. And when it contracts, transfers blood to the ventricle, then the ventricle will contract, that will take certain time, 150 millisecond, okay, and then only 150 millisecond, sometime it will take, and then it will contract and pump the blood away from the heart to the body, okay. And then this pumping action of the heart is regulated by a pacemaker region called sinoatrial node, SA node they will call it, okay, SA node, located in the right atrium. An electrical impulse is created in this region by the diffusion of calcium ions, sodium ions and potassium ions across the membranes of the cells, okay. There is this figure will tell nicely, okay. Wait please. I will come back, I want to show you something. Oh, this is normal ECG. Okay, this gives you the action. Okay, so you know the scale, this is 1 millisecond. You are at negative 70 millivolts, okay, 0 and plus 30. So initially you are in the resting position, okay. Then at negative 55 you get that impulse, okay. So sodium channels open here, okay, this from negative 70 to 55, sodium channels open, and then you get the depolarization, more sodium channels open, okay, it goes to plus 30 or 20 millivolt, okay. Then sodium channels close, okay, because lot of sodium come into the cell, now you have to compensate it. So, potassium channels open, okay. So, they will flow outside, this will come in, this will go out, so to compensate for the charging, okay. So, at that time this is depolarization, repolarizations comes back to almost to the original value and they will stay there, okay. It is like, remember when you have voltage, there will be some overshoot and undershoot, that is kind of thing, okay. So, it cannot exactly stay here, and then again the next impulse it will go. So, this is what it is, okay. Sodium channels open, more sodium channels open, and then they close, and potassium open, potassium close. Then this cycle keeps on going, and you know this happens 72 times per minute, okay. Questions? Now I will go back to where I was there, because that is a good slide, I should have put it here. Okay. Okay. So, as an electrical impulse is created in the region by the diffusion of calcium, sodium, potassium ions across the membrane of the cells, impulse is created by the motion of these ions first transferred to the atria, okay, that is the P curve, causing them to contract and push blood into the ventricles. After about 150 millisecond, okay, the impulse moves to the ventricles, causing them to contract and pump blood away from the heart into the body. As the impulse moves away from the chambers of the heart, these sections relax, okay. So, contract, pump, relax, contract, pump, relax. Using EKG allows doctors to measure the relative voltage of these impulses at various positions in the heart, okay. This is possible because of the body is a good conductor of electricity. When an electrical potential is generated in one section of the heart, okay, an electric current is conducted in the body surface of a specific area. So, we can measure in almost any area. Electrodes are attached to the body in these areas and then enable measurement of this.
You have the pointer here, okay, the laser pointer.
Okay. Okay. The electrical signals measured by ECG have been characterized and represent various phases of the heartbeat. Each time the heart beats produces 3 distinct ECG waves. Okay. The first is called the P wave. This measures the electrical signal generated by the pacemaker, okay, sinoatrial node, and then the next pulse is the largest signal called QRS complex. This segment represents the electric signal created by relaxing of the atria, contraction of the auricles, okay, ventricles, and then comes, okay, completing the cycle is the T wave, okay, which signifies relaxing or repolarization of the ventricles. The characteristics of the heart corresponds to the QRS complex and the T wave. Okay. Then EKG provides useful data, can help defective various problems related to the heart function. Okay. Find heart rate, measuring distance between the peaks, and then diagnosis of certain medical problems, and then patients with high blood pressure, amplitude of QRS complex is significantly increased. Okay, that area will be high. So, we can know that one. The balance of certain chemicals in the body can also be detected by ECG, as amplitude of the signals is related to the level of chemicals in the body. Okay. Damage in heart can be easily observed by the deformation in the Q wave. Okay. The most useful characteristic of ECG is ability to detect and describe arrhythmia or abnormal heartbeats, and then also used for observing obstructions in the arteries. This is typically done by looking for a depressed segment between S and T waves. Okay. This is what happens, okay. How, you know, atria, it contracts, sends to ventricle, ventricle contracts, sends that. Okay. So, that is P, then QRS complex, then T, repolarization, depolarization, then repetition of the same. If there is any change in this, the number of pulses, the magnitude, the height of the P wave, the area of the QRS complex, everything is a message, information telling you whether you are fine or not. For that we need to measure accurately, correct. If there is any artifact in our measurement, we will relate it to our heart. Okay. This is where we come into picture, that how exactly, how closely, how accurately we measure. There will be always some error. Okay. We cannot measure anything 100%. Okay.
Everybody
As
understands artifacts? Anybody who does?
okay, what is artifact means?
Disturbances in the signals or in the
Disturbances happen in the measurement, not in the heart. Huh?
Okay.
Time up?
No, no, go ahead. We have another 10 minutes.
Oh God. Okay, maybe I will skip all this. I will go back to measurement. Okay. This and all, and skip. I put all that in, at least you can see it. Okay, P wave is the artificial, this is good, artificial depolarization, QRS is the ventricular depolarization, T wave is the ventricular repolarization. What is depolarization means? Depolarization means increase in the voltage, okay, concentration changes of the chemicals. Okay, the PR interval, the QRS complex area, the height, everything is important. Okay. So these two slides, you can read, it gives you all the details, how long it takes for each one, okay. Time in millisecond, ECG terminology, conduction velocity, intrinsic frequency, okay. So you can see that how the various parts are involved, okay. And it is not, as an engineer, we do not want to do this. Okay, so here they talk about two types of leads, bipolar and unipolar. Unipolar is one point on the body and the other one is the reference point with 0. Okay, so what we do this one only, three leads. We do not use we use 2 different points and then ground. We use that one. Okay, we do not use 12. We do not want. Okay, here is our wonderful ECG. Okay, where does Ecg Amplifier, okay, design example. This is from John Webster's book. This is the Bible of this medical instrumentation. Okay, so you see here, everyone recognize this. This is the instrumentation Op-Amp. Okay, you have the Op-Amp, you have the, what do you call this when you go back? Feedback, no? Huh? Negative feedback, no, this is different. What do you call that? Buffer, no. Okay, I will tell the name later. Okay. So yeah, we have to do some exercise about Op-Amp. Okay, anyway, you see that this is the instrumentation part. The
Sandeep, identify.
So this is your differential.
No, but what configuration is that?
This is your high pass filter, low pass filter. Okay. Here I want to tell you one thing. Try to maintain this structure, maintain this value for anything you design. That way our work will be really easy. Okay. Here if you see this one, okay, this is a differential Op-Amp. Everyone sees that? So okay, so what is the gain of this differential? What's the gain?
RF by R1. Like RF feedback ratio divided by input ratio.
What is the gain of this amplifier? You have
Values
all the
are given
values.
there, no?
You have all the values. What is RF? RF is 47, R1 is 10, 4.7. Okay, here this is a instrumentation amplifier. Okay, so does anyone remember the equation? 1 plus
2 are divided by
RG. Okay, 1 plus, very good, 2 times 22 divided by 10. Okay, so 2 times 22, 44 divided by 10 is 4.4 plus 1, 5.4. So this pre-amplifier stage has a 5.4 gain, this one has 4.7 gain. So totally it will have 25 gain. Okay, and then here if you see it is 150 kilo ohm divided by 4.7, it will be how much? Can someone calculate that? 150 divided by 4.7, how much? 32, okay. So he rounded up nicely, 25 times 32, 800, this is the gain of this one. This is typically your Ecg amplifier will be 800, 850, 900 is the gain, okay. So that is the value I want you to know. And then everybody remember CMMR, common mode rejection ratio, you want it to be as high as possible, okay. So when you pick up what is the, we are going to use 741s, correct, in the lab. What is the CMR of 844, 741, anyone remembers? It is more than 80, that is good enough for our purpose, 90, okay. So 86 dB and more, okay. And then we are going to do 0.04 to 150 hertz, okay, plus minus 3 dB and flat for 42 hertz. So we are going to use, this is our high pass or low pass filter range. This is going to be your high pass, no, anything above this you want, and then anything below this, okay. So this high pass is here, okay, and then this low pass is here, this 0.01, okay. So when we build, we are going to build the same thing, okay. Eeg, what will happen, remember it will be like 10 microvolt, you want at least 2 volts, okay. So it will be like 60,000, so you cannot build in once, okay. Why 800, why can't we have like 800 meg and 1 meg here, why we are splitting into stages? You will see all that, okay. So for Eeg the difference will be, you will add one more stage.
See, the question is, why aren't you amplifying in one stage, why are you doing it in stages? Yes, Subir? No, forgotten the analog electronics, yeah. Antar, huh?
Losses.
Well, losses, what kind of losses?
Power loss.
What loss?
Ma'am, if we use a higher resistor, there will be some I square on losses.
What is the current there, what is the voltage? Noise is the main thing, okay, because remember it can pick anything, correct. So it all will be amplified. So normally you keep the initial one as low as possible, then you will have higher one, okay. So similarly you want like say 65,000, so you have 800, okay, 800, 65,000 means, oh sorry, okay, you have to multiply that. So okay, so we will have 3 stage for Eeg, remember that, under no case we can have only single stage, 2 stage, minimum 2 stages for Ecg and EMG. Eeg you must have 3 stages, if you put 2 stages you are no partial credit also, because I am telling now 0, easy for me to grade. So we will build all this tomorrow, okay. So here it is, I have put you all the details there, okay. So actually it is 825, that is okay, remember the parts will not be exactly the value, there will be some tolerances, so we can have it, okay. So we are going to build this one and then we will measure it. Okay, so I do not want to go through all this. We will start, how much time we have?
You have 5 minutes for the break, if you want we will take the break and then start.
No, I will complete this, everybody remembers, correct. So we will start with the problem, okay. So I will complete this, it is all repetition. See, this gives you nicely, okay, comparison, biopotential, the name of the biopotential, the magnitude and other details, what are the problems we encounter, okay, moderate gain, bandwidth, noise, CMRR, input R, okay. In the case of Eeg, high gain, very low noise, filtering. This is what we have to consider, okay, these are the requirements. And then EMG, cool, it is gain and bandwidth of op-amps. And then EOG we will not do it, but anyway you can do, no, it is DC and low drift. Additional features to be desired, okay, electrical safety, isolation, defibrillation protection. This is what main thing, okay, because we are doing it on the patient. So we have to make sure grounding is paka, isolation is there, they do not talk to each other, okay, everything. This is where the biomedical features come into picture. Up to this it is electrical, we can build whatever. So you have to have short leads, nicely sitting, neat, okay, neat looking. So let me see how you build, because that will contribute to your noise and picking up, each wire will be like an antenna, it will pick everything possible. Okay. So, that is where you come into picture. Okay. Sorry, normally I do not get a phone call when I am doing
Anyway,
some.
you can give a break now.
Yeah, wait, let me finish it. Please give me 1 minute. Okay, filter and all you do not want it. Okay, so there are isolation, protection. Electrodes. Okay, we are going to use what is called the ECG resting electrode. Okay, so we will use this one. We won't use this many. Okay, so this one only we will use, and I will tell you how to use them when you put it on your body. Okay, with this I stop. I will stop the phone. Please ask any questions. Yeah.
We have a break now. We'll come back and then do the problems.
Anyone else?
One more is left. It's okay, start.
Who? He left? No, he's here. We'll wait. No, that won't be fair.
Actually, it is getting live stream, so it is. If we are waiting, we are making people wait elsewhere too. Remember that. Okay, that is the most important point. It's not only that it is only for you, it's getting live stream.
Okay, let us refresh. Okay, op-amps. What are the various types of op-amps? Why it's called op-amp? What kind of operations it will do?
Mathematical, any mathematical.
That is not the right answer. Give me the operation.
Logic.
Huh?
Addition, subtraction, integration.
Everything. Okay, operational amplifier. So there is nothing it cannot do. Okay, so we know it basically will have two leads, minus plus. Okay, and then we will have plus minus 15 voltage. What is the major drawback of an op-amp? You need two bipolar, okay, plus minus. That's headache, correct? So, unipolar ones. Yeah? How does it work, unipolar one?
Maybe we can increase a plus up to 30 and a minus up to 0.
What big deal? You are still using external agency, okay? That is why it is an active device, correct? Resistor is a passive device, capacitor is a passive device. It is an active device, you have to put, okay, energy into it, okay? So, Vn, and you can ground that, you can do many things, okay? This can be anything, okay? So, there are majorly some few types of op-amps. Can someone list them? What are the types of op-amps? What is that? Inverting, correct? And then non-inverting, and then summing, and then differential, and then instrumentation. This is what we are interested in this course, so we will talk about these things. Okay, so you know all about this instrumentation, summing and all that. Okay, I will test your knowledge by giving a problem. Okay, so and if you cannot do, I will tell you how to do that. Okay, so build or what yeah, implement V out equal to 5 V in. Okay, V out equal to 5 V in using these 5 kinds. I know I write small, that is all right. Using inverting, non-inverting, summing, differential, instrumentation op-amps. Okay. And then from here we will go to the Ecg. Sketch it, okay, and sketch, mark each and every part, okay. So I have the solution here, so I know how to do it. I want you to do it. Follow it. If you don't, you can discuss with your friends everything. I have no problem. Talk to each other, help each other, and then come up with it.
You just carry on. I will just come back in 15 minutes.
Yes, please.
Using all or anyone? Using all of the configuration or
Yeah. Using everything.
How do you use all of them? You are going to use one by one. Okay? first one.
It's not complete. No, it is, that is. What's the V out? V out is negative, no. So put one more stage. You need V.
Okay.
I want 5 Vn, not negative 5 Vn. You cannot have negative, no. That is not correct. Okay, your input is Vn, not negative Vn. So when you do the first one, you need to have 2 stages.
Input is negative, input is buffer, then input is
No buffer. Input is Vn. I want output 5 Vn, not negative 5 Vn. Huh? So this is solved. Negative plus, correct? So this goes there. Is this correct? Did anyone do this? Now what value should I use here? Give me.
1K, 1K.
Why not I use 2K, 2K?
Oh, yes.
Technically correct, practically not correct. Why? You have to buy a 5K, you have to buy a 1K. So your goal should be reuse. Okay, so either use 5K or 1K, don't use 2K, don't use 10K, okay, just because you have it there, okay, normally, so that's one point. And then again, why I am using K, why not I use 5 ohm and 1 ohm? Why I have to use? What is the limitation of op-amp? What is how much amperes it can take?
Practically 0.
20 milliamperes max. So you limit the current to, that is nothing like 0. 17, 18 milliamperes, okay. So you have to keep it within that. That's why we keep in kiloamperes, okay. So minimum is 1 kiloamperes. You cannot use anything smaller than that, okay. So this is my inverting amplifier. Everybody got it? Okay, you have to have 2 stages and I will put 1K, 1K. Use any one of these values here, only here, don't use new values, okay. That is an important aspect, practical aspect, okay. Technically you will be correct, but otherwise, okay. So I think everybody knows inverting now, non-inverting, correct. How do we do non-inverting? Okay. So what's the value here? Very good, okay, very good. So we are done with this. Summing amplifier. So how do we do summing amplifier? Where is the summing coming from? You can ground, okay. So some people do, I know I have seen students doing 2.5 times 2.5 like that, and I find this to be very easy, you ground one, but yes, here you have multiple answers. Okay. Next, differential. Maybe I'll erase all this. I need more paper towel. correct, V2 minus V1. So, this is going to be 5k, 1k, 1k, 5k, correct. If you see your book, he has used a pot here. So, you put a 10k pot so that you can accurately, this will compensate for any variation. So, you can use a 10k pot and then you can adjust very nicely, that way you will get very accurate. So, that is one of the ways. So, V out equal to, in all the time you have to write V out equal to 5 times V in. Make sense? Questions? Now, what is this called when you have this kind of arrangement? Sorry. Oh, you call buffer, it is called voltage follower. So, why do we use this? For instrumentation, that is the difference, correct. We cannot take directly here because of the low input impedance. So, because the op-amps are noted for very high input impedance, low output impedance. So, we will have this voltage follower. This is how we do that instrumentation op-amp. This is what we are going to do for our Ecg, EMG, Eg, all that. So, so V in 1, V in 2. Then comes the differential op-amp. Here because I put 5k here, 1k here, 5k here, 1k here. What happens if I want to use this for something else, some other gain, can we use it? No, we have to rebuild the whole thing. That is when that configuration came. Remember, we used that in the Ecg circuit, where you will have this fellow and then you will have this one and then you have the three of them. That is so it is R1, RG, R1 and all those things comes. So, we have 1 plus 2 R1 divided by RG is your the pre-amplifier stage gain, then comes the differential amplifier, then comes the high frequency, high filtered, then comes the low frequency and then another stage. You understand? So, this is what the instrumentation op-amp. We can buy this whole thing in one, which is called IN, but normally in many labs we get, what is that, 741s, correct? So, we can use 3 of them. We build both ways, we got almost similar results. So, I tell the students do whatever you like, I do not restrict, but many people do this. Otherwise, you can buy one chip, it will have all that, just you will have the input to one, you can adjust the RG and then you can go ahead. Is it clear what I am talking? Does it make sense? Questions? Now let us design a Ecg amplifier. Any questions? Everybody is fine? So, now you will do it based on, maybe we should open that page, no? I will keep that thing open. Based on that, similarly you do for these values, then we will build either this or that, your choice, whichever you like. So, again this is a worked out problem. So, I have the solution. Design an Ecg amplifier, gain 1200. Try to use those numbers. I don't, anyway, V in is 4 millivolt. So, you know what is the V, then CMR greater than 90 dB. band pass is 0.2 hertz to 60 hertz. Okay. Indicate all assumptions. Okay. Try to use the same value, only you have to change only the second stage. Keep the first stage as is because we know it works. Okay. I will open up the Ecg example. So you know the gain is 1200, 4 millivolts. So you know what's the output you are expecting. CMR is 90 dB or above, 0.2 hertz to 60 hertz. Make sense?
So why is that input voltage is specified in
Yeah, it is redundant.
from the sensor? I mean, how is it in our control that what voltage will be getting? And that too for
Actually you do not need it, but that gives you, okay, when you build this, okay, you can put 4 millivolt and measure output and see what happens.
I mean, from design perspective, it is not required.
Correct. That is another thing. You will have redundant information, does not mean you have to use it. Make sense? Yeah, I have seen, but sometimes I give all the values, people try to use that. Not necessarily. That shows me whether you understood or not. If I give something, if it is redundant, you do not have to use it. But anyway, we are learning, so you can ask or you can do that. Make sense? Please do this first, then we will do a EEG, because EMG is similar. Okay, so we will do EEG, then we can go home. So I will open that, follow the initial stage, the same thing. Okay, the pre-amplifier, everything. Use the 22 kilo ohm, 10 kilo ohm, keep that 5.4 and then the 4.7, all that, and then only change the second stage. Here. Maybe now I should switch off the light, I guess. Can you see properly? Maybe we have to move this. Thank you. Oh, you lift like that. Next time I will. Everybody note down the values. Gain is 1200. And then Vn, you don't need CMR also, you don't need. You only need the frequency bandwidth and then the gain. Oh, I brought some chocolates. Oh, no. I hope we have enough. Where did I keep my notes?
This is to be done individually with the inverting, non-inverting amplifier.
With using the instrumentation.
Same actually.
Yeah, instrumentation, then differential. Okay, because that way you can avoid the loading of the system. Okay, so first is the pre-amplifier stage, then the differential amplifier, then the high frequency filter, then low frequency, and then another second stage, 2 stages. Actually 3 stages if you count exactly. Sure. Try to use the same resistors everywhere. Okay. Remember, normally to calculate the frequency filter, it's easy to to vary the resistor than capacitor. So follow the same value. Keep the capacitor constant. Calculate the resistance. Okay. Sure. Oh. So the only variable you will have is these two values. Everything else should be similar. Keep 1 microfarad and 0.01 microfarad. Just vary the resistances. No, you don't have to get it. Sure. And I hope you remember approximately the standard resistance values, okay. So we can, otherwise you put a pot, okay. If it's variable resistors, you know how to represent, you put a resistor with a arrow so that you know it's variable because you don't have a standard value. So where are we? Did anyone calculate the filters? The low pass filter, what is your value? C is 1 microfarad. You know, first you have to calculate the filters, correct? Everything else is same. You draw that later. First calculate all the values. First do the two filters because that decides your resistance, that decides your gain selection. Okay, everybody knows how to do the filters. Remember, the filter means that you want the critical frequency. So the value of the resistance should be equal to the impedance of the capacitor. So R equal to 1 over 2 pi Fc. So F you know, okay, C you know, 2 you know, pi you know. So find R. Okay, and then round off the R to a normal value and then replug and make sure F is within that limit. Okay, that's how we do. So in my case, what did I do? Fc equal to 0.2 equal to 1 over 2 pi RC, C equal to 1 microfarad, so R equal to 0.8 megaohm I got. Did anyone get 0.8 megaohm? So convert to 1 megaohm. The first one. For 0.2, okay, the high pass filter 0.2 equal to 1 over 2 pi RC, C is 1 microfarad. So I get 0.8 megohm. Where are you? Where is everyone? Do you understand what we are doing? Okay, take your time. Maybe I am rushing you. Maybe we need the board. Sorry. Everybody understands what to do, correct? Yeah. You can sketch the value, the circuit later. Sketching the circuit is, no, it will be too far. Maybe we need both. Maybe you can put that closer. Yes, thank you. No, it's 0.2, correct? 0.2 is 1 over 2 pi RC, correct? C, what's that? R equal to 1 over 2 pi Fc, F equal to 1 over 2 pi RC. So you put C equal to 1 microfarad okay, or equal to 1 over 2 times pi times 0.2 times 1 meg ohm, correct? Because this is micro, I am going to get in meg. So 2 pi times 0.2 is how much? Two times 5 times 0.2 is 1 over that. 0.79577, so 0.8 meg ohm. Did everyone get 0.8 meg ohm? Is 0.8 meg ohm standard? I don't think so. I can use 1 meg ohm. Okay, if I use 1 meg ohm, am I in the right range? So what do? I go back, F equal to 1 over 2 pi, R is 1 meg, C is 1 micro, micro meg cancels, 1 over 2 pi, correct? 1 divided by 2 divided by pi. 0.159, am I within the ballpark? Very much, okay. This is how we do, okay. We use this equation first, pick an OR, is standard OR, and then we go back, make sure we are in the right ballpark, okay. Similarly, you repeat this for F equal to 60, correct? 1 over 2 pi or C is 0.01, correct? Microfarad, again I will get it in meg. So when I do that one, I am getting, how much you are getting? 0.26 meg ohm, okay, which is 260 kilo ohm. So we can have 430 because they had 470K, I am going to use 470K, okay. So if I use 470K, again go back and calculate 1 over 2 pi 0.47 meg times 0.01 micro. So meg and micro cancels. So 2 times pi times 0.47 times 0.01 1 over x. I get 33.86. Is that right? No, 61.2. Okay, yeah, here, okay, I have used many values here. Maybe 330K we will use. Okay, we will use 330K. Actually 220 is smaller, no? We need a 0.26, 260K. 260K is the value, so closest is 330K, okay. So then you get how much? Or you can use a pot and adjust it, okay. So 2 times 5 times 0.33 times 48.23, that's fine. If you want to be very accurate, put a pot there. 260K, 260K, the nearest standard is 330. 270? Oh yeah, very good, 270 is fine. Okay, oh yeah, we will be much better now. 2 times pi times 0.27 times 0.01. 58.95, 60. Oh God, we are accurate. Very good. Is everyone getting this? Everyone in the same? Am I going fast? Okay, so now we go back over your circuit. Now you draw the circuit. Okay. So this one is how much? 25, correct? 25 is this one. 1200 divided by 25 is how much? Actually, it's slightly 5.4 times 4.7, correct? We will use exact values, 25.38, okay, that's fine. 1200 divided by 25 is how much? 48. So you have your so 48. Then we can use a, I know 47 is there, how do we get 48? Or we can slightly tweak the first stage, instead of 22K we can put 33K there. Then we will get 2 times 3.3, correct? 1 plus 2 times 33 divided by 10, 6.6 plus 1, no? 1 plus 7.6 times 4.7. $35.72. Let me see what I did. Oh, I used 22. Okay, what I did, I put RG 6.4. I use a pot. Okay, so if you use RG 6.4, what happens? You get 37, I guess. So then I use 47 here and 37 here. Anyway, you can play with this. Yeah, everywhere I use that one. I use 330K 0.01 microfarad, 10K 1 megohm, 1 megohm, 1 microfarad, 47K 10K, 47K 10K, 22K, 6.4K, 22K. Yeah, I did the reverse engineering because I wanted here to be. Okay, I use the 330K, okay, 330K and 10K, so 33. My stage 2 gain is 33, okay. So, my gain, the stage 1 is 1200 divided by 33 is how much? $36.36. Okay, divided by 4.7 is. Yeah, I am purposely writing like that because I want you to do 7.74. Okay, so 2 times 22 divided by x 1 plus equal to 7.74. So minus 1 is 6.74. So 2 times 22 divided by 6.74 is 44 divided by 6.74 is 6.53. Figure it out because I purposely do this way. If you have question, ask me. Who got it the way I did it? Remember we have 330 kilo ohm, so I put a 10 kilo ohm there, okay. So 330, my second stage is 33 by gain, okay. And then, so I am changing the front end, okay. So again I am still keeping the 22K. So I just change the RG, okay, RG keep it as X and then find out what you need. Does it make sense? Who got it? You sketch it, I will see. Where are we? Okay, very good, you got it, 260 kilo ohm, okay. Okay, so you can use 270 there.
Yeah,
270 is standard, okay. So we calculate it's fine. So no. You say equal to, put an arrow and yeah, because 270 is standard. Very good. Okay. So do this for the other
So
students.
this 2 stages, no?
Yeah.
So first one.
So this is point. This is okay. So this 1 farad. So here, okay.
Yeah.
This is high frequency. So you get to 1 microfarad, 1 megohm.
Yeah. 1.
Okay. Similarly, you put 1 megohm here because they have to be same. And then here you got 0.01 and here you got 270K, correct?
Yeah.
270K. So if you put 10K here, you have 27. Your gain is 27. So you change here.
So this 27 is to be considered
Yeah.
in the total gain.
Yeah. This is the second
This
stage.
is a 3-stage kind of.
2 stage means this is called 1 stage. This is pre-amplifier. Okay. If you take this is instrumentation, the whole thing is called 1 stage. If you want to be perfectly accurate, you want to call this pre-amplifier. This is the amplification, this is pre-amplification. Okay? Yeah, so you can adjust here or there, whichever.
So this should be 27.
Yeah, actually, yeah, maybe we can adjust here, this one we can keep it. Yeah, it depends. On the day I felt like that, I did that. Okay, I see one got it. Where are you?
I was earlier doing with
This all done, it's all we assume the op-amp has it, okay. If you use 1 microfarad, did you get,
59.
no, check it out. You should get 0.8 megohm. See, I got, 1 over 2 pi, 0.2 times 1. 1 micro is, I put the meg here. So you have all the numbers here. You should get 0.8 megohm and 1 meg. Okay, he is done. What about you? You got it? Very good. Everyone understand the concept, if not the numbers? Okay, no. Okay, where's the problem?
How exactly you calculated that? You have to put this resistors in this formula, right? Then how you are calculating the gain? Gain we have.
This one gives you 1 gain.
Hmm.
This one gives you 1 gain.
Hmm.
Then remember this is my high pass, so this is what 1 microfarad, correct? And this is 1 megohm. Okay? Because I have 1 megohm here, I want to use the same here, correct? 1 megohm. Then 0.01, this is 270K. So now you can put either 10K, then it's 27. So 1200 divided by 27, you can implement there. You can keep this same, okay, 1 plus 4.4, so you can adjust this value. Varying this will be the best bet, least working, yeah. Change this to get whatever you want, okay. So 27 times 5.4 we have. So 1200 divided by 27, how much? Put that here.
44.
Okay.
44? It cannot be 44. No.
1200 divided by 27.
27 divided by 5.4.
Into 5.7. Divided by 5.4.
8.2, no. How do we get 8.2? You put a pot. 8.4, 84K. Yeah? Put a 100K pot, 10K here, 10K here, 100K here. Make sense? So yeah, this is good. I did too much unwanted calculation. Today it occurs to me. Okay, next time I know what to do. Keep this same. This one you calculator.
Overall
So
gain should be 1200.
correct, exactly. Yeah, no, each student does
I should
differently.
fix this one and vary this one.
No,
Initially.
we should fix this one and
Keep this same because it's instrumentation. It's easy. Just keep this is fixed based on this frequency. So this is easy to play with it. Very good. I learned this today. You understand? Got it?
this part, I mean, you calculated this
This we
based on that
calculated now.
Based on the
frequency.
correct.
And what about these two?
Remember, this is in the lower arm of this one.
This also comes from this frequency.
No, this comes from this frequency.
Exactly, the one
Yeah,
of the cutoffs.
but
This
you
this
want-
is the this is the high pass part. This part is the high pass part, and then from that we're getting this this resistor.
Yeah, this
Fine.
is. Yeah.
And when we're talking about this capacitor on the other hand for the low pass part, from that we're getting this resistor.
Yeah,
I'm talking about these two.
these two. Okay.
No, this one and this one.
Okay, this one is you have 270K here. So typically you can put 10 so that you get 27K easily directly. Okay, that's it. You can put anything there. I put 10 because I know 270 divided by 10 gives me 27. So I can vary here.
Okay.
And then because this is this portion. In
And
this
what
arm,
about this one?
symmetry.
Symmetry.
for
Okay.
maintaining the
That's it.
Current.
Good. Yeah, ask me a question. This is how we learn. You got it.
Yeah.
You got it. You got it. You got it. Okay, now with this knowledge, let's do one. Then you got it? Yeah.
Up to here I have 1200 by 33 you are
Okay,
using
use
330 kilo ohm and 10, that's why it's coming 33, you are using 33, right?
No, here I shouldn't be using 330K, because we didn't use, this is you can pick some gain whichever is suitable. Hmm? See here we have 270, you 10, so you have 27. So here you have 5.4, correct? So 22, yeah, it's 22, 1 plus 22 times 22 divided by 10, 4.4. 4.4 plus 1, 5.4. So 27 times 5.4 times x equal to 1200. So get that x and put that. Because we put 1 megohm here, to be symmetric we put 1 megohm there. That's it. You understand? Yeah, I want each and every value why we got, how we got it. Make sense? Questions? Oh yeah, Sandeep, I didn't check yours. You got it?
Yeah, what I did, gain 1 into gain 2 we have 1200. So yeah.
So you
I'm
did
able
your
to-
way.
Yeah, I did my way.
Okay, no problem. Just show me the values.
I'm-
No alpha or 6. Put the numbers. Put the numbers. Put exact values there. I don't want alpha and I don't want read there. Put the values there only. You got it? Where is it? Put it there. When I see that, I have to see. Okay, let's do the next problem. Those of you. Now we build a Ecg amplifier. Okay, I'll give the gain directly to save you time. 65,300 because I think we did in one case. Gain is 65,300. I don't want Vn, you don't want that. Okay, indicate all assumptions. What are the assumptions you made? We made that the op-amps are ideal, no, they are practically good, okay, means very high CMRR and all those kind of things. Okay, so that one important, indicate the assumptions. Okay, and again why the first stage preferably preamp, okay, the pre-amplifying stage you want low because any noise it picks up you don't want to get amplified. Okay, so that is why the later stage can be higher value, the initial stages should be lower value. Okay. So let us do, what is the frequency for Eg? 40, no? Let us do from 1 Hertz to 40 Hertz. Okay, gain is 65,300 and F is 1 to 40 Hertz. Just do this. Now you know how to do this. Okay. Yeah. So you know what you can do if you are smart? Tell me what you can do. You just did 1200, correct? 65,300 divided by 1200, find out how much it is.
Use it as an initial stage and
How much? 54. Can we have one stage at 54?
Another stage added at the end.
Yeah.
that's it.
Okay, so always remember that's what they do in semiconductors, correct? You build 4-bit chips and then you add that. That's what we will do. We are not any less than anyone else, correct? Actually, we are better than many. Because they say, electrical engineering, you cannot taste it, you cannot touch it. How do you feel it? Still, we have to study it and ace it. You understand? So you can just reproduce the existing circuit, just add another stage. I am giving you all short tricks and tricks of the trade. And then EMG, just change the frequency.
So you want us to do like that only? Just
No, I am just giving you some maybe unwanted tips. You do whichever way you want. Huh? When you build, it has to work. That's all I care. I don't wonder how you do it. Just do it. It has to work. You want chocolate? I gave to everyone else. Yeah. I have more at home for you. Oh God, I'm talking all this with the mic on. The mic on, I am talking. It's the time.
today's time is over.
They can finish and go. Their choice. Maybe that can be in a homework problem.
Huh?
That can be homework. Can I give this one as the homework?
Yeah.
You can either finish and go or this is your homework number 1. Okay, it's easy, no? You all can ace it. Everyone gets 100 out of 100.
Yeah, one thing, I hope all of you are having access to the net in some form or the other. Wi-Fi is there in the guest house. Otherwise, okay, so the spectrum paper, because once you are logged into the institute network, we have IEEE Explore is available. So you can download such the spectrum paper in 2012. 2012, no?
I don't know, just put muscle stimulation, okay, Louisville. I will find out otherwise. Or you can find out now. It should be there in my muscle stimulation lecture. I have to go check it out. Shall I switch off the thing? Over now.
Yeah, I think you can stop the recording.